Good morning. In the previous section, we have discussed regarding the analysis and performance of three-phase induction motor. Today, we are going to discuss about the remaining part, that is part 2. In this, I am going to discuss about the operation of the induction motor when it is supplied with the unbalanced voltages, and operation of the induction motor on single phasing. And the third point, we are going to discuss about the unbalanced rotor impedance operation. Unbalanced rotor impedance operation. So again, I'm going to share some documents. So in the previous, we have discussed about the particular torque equation of a motor. So in this, you can see this is the basic torque developed by the motor. So this one already we have derived. And then what will be the slip for the maximum torque? So this is again slip for the maximum torque. We have differentiated the particular torque with respect to S and equated it to 0. So we have got this particular the slip for maximum torque SM. So in order to get the Tmax, so we have substituted in the T equation S is equal to SM, and we have got Tmax, that is maximum torque of the induction motor. This is the equation of maximum torque of the induction motor. So again, we have discussed this particular characteristics curve. So that is along the x-axis we have taken the torque and the rotor current, and along the y-axis we have taken the angular speed of the motor. So here we have got two equations, that is for T and for the IR. So in this case, in this particular curve, so there are two axes, and there are, let us say, this quadrant. So this quadrant, first quadrant, so here whatever the operation of the motor is there, it is forward motoring. So this is for omega ms. So this thing, this curve, and it is 0 omega ms, omega m is equal to 0. This is positive omega ms, and this is omega is equal to 0. And if I draw this here, this is negative direction, and this in this case whatever the omega is there, it is minus omega s. So this is this particular, whatever the operation of the motor is there, so it is forward motor. So this is about the torque slip characteristics. So now we'll go with the operation of the three-phase induction motor with the unbalanced source voltage and single phase. So in this case, whatever the induction motor is there, it is connected to three-phase supply. The stator of the induction motor is connected to three-phase supply, So in this case, uh, the voltages can be split into the positive, negative, and zero sequence components. Whatever the VA, VB, and VC, uh, the voltages, these are the say unbalanced voltages. So these are uh, split into their positive, negative, and zero sequence components. So here, what is VA? So the VA is given by this VA. It is given by, if I take VA, it is having VP plus Vn plus V0. That is each voltage VA, it is having positive component, the negative component, and zero component. VB is also having positive component, negative component, zero component, and VC is also having positive, negative, and zero. So if I take this particular positive, negative, and zero component, then I can write uh, as this VA is equal to VP plus Vn plus V0. This VA is equal to Vp plus Vn plus V0, and Vb is again Vp plus Vn plus V0. It is for phase B, and it is VA, uh, that is Vp plus Vn plus V0 for the uh, phase C. So now we can write these equations. That is Vp is equal to 1 by 3 Va plus alpha V plus alpha square Vc. Then Vn, you can write 1 by 3 Va plus alpha square V plus alpha into Vc. And zero sequence, it is 1 by 3 Va plus Vb plus Vc. So what is alpha here? In this case, alpha is an operator, or it is exponential 120 degree. This operator rotates, that is then 120 degree. So this alpha is a operator. So now this is equation number 1. This is equation number 1, and this is equation number 2, and this is equation number 3. Equation number 3. So here we are having unbalanced voltages. When we have the unbalanced voltages, a set of unbalanced voltages, so we have no direct clue on how these unbalanced voltages will affect operation of the induction motor. So we don't have any clue on how these unbalanced voltages will affect the operation of the induction. So by taking help of sequence components, uh, we can break down the unbalanced voltages VA, VB, VC into positive, negative, and the zero sequence component. Please remember. So we are breaking down, or we are splitting the VA, VB, and VC into the positive, negative, and zero sequence component. So the values obtained are here. These are the values obtained: VP, Vn, and V0. Since we assume that our system is linear system, we are applying the superposition theorem. We are applying the superposition theorem. So here, apply positive, negative, and zero sequence component on the induction motor. In this, what we are doing is the zero sequence component does not produce any torque. If I apply this positive, negative, and zero sequence component on the particular induction motor, the zero sequence component does not produce any torque. So it is eliminated. Eliminated. So now let us see how this voltages affect on starting of the induction motor. So let us take first the positive sequence component. Positive sequence component. So if I take positive sequence component, what will be the the rotor current IR dash P rotor current for the positive sequence component. So here same we are writing here Vp, the positive sequence voltage, Rs plus Rr dash divided by S, Rr dash divided by S, then plus J XS plus XR dash, XS plus XR dash. So here whatever the slip you are getting, it is positive slip. Please remember the slip is, it is positive slip. So now uh, this is the equation for the rotor current I dash P. Now go for the TP, it is torque for positive sequence TP. So again it is 3 divided by omega ms xp Vp square Ri dash divided by S, Rs plus Ri dash divided by S square plus Xs plus Xr dash. Uh, Again this is TP, this is TP, positive sequence torque. So now go for the negative sequence component. Go with the negative sequence component. So again, in order to have the negative sequence component, so let us go for the slip. So in this case, what happens? In case of the negative sequence component voltages, so whatever the negative sequence components are there, so they rotate in the reverse as that of the positive sequence component, as that of the positive sequence component. So what we can take is whatever the WSM was there, so it will be minus WMS, minus WMS. So whatever the RMF which is rotating, uh, so with the speed of the WMS, now in the case of negative sequence voltage, uh, it is rotating in the reverse direction, that is minus. So now the slip will be given by minus omega ns omega ms minus omega m divided by minus omega ms. So it is 2 minus s, 2 minus s. So with this equation for slip, following equations are obtained, that is ir dash n negative sequence and again tn. So just you have to put yes instead of s, you have to put 2 minus s. So these are the two equations you can get. So now the RMS current and torque are given by here in this case. So whatever the particular RMS current, that is the total current, and the torques are resultant of, see, IR dash is resultant of positive sequence and negative sequence it is, and the torque will be again resultant of TP plus TN, TP plus TN. So if I take T as this, this is the resultant. So in this case, in the particular unbalanced operation, uh, whatever the curve we are getting, so this is the curve. So again it is omega m and versus torque. So here whatever the curve we are getting, it is say for the positive sequence, and whatever the curve we are getting, it is for the negative sequence, it is for the negative sequence. So our total t, resultant t, will be it is uh, the reducing, it is reducing, uh, so and it is less than that of the uh, total torque what we have got previous. So this is the net torque. So the net torque is reducing here. So due to the unbalanced stator voltage, what happens? The net torque of the motor reduces, and once the net torque reduces, then the power output will reduce. Power output will reduce. This is the effect of unbalanced stator voltage. Unbalanced stator voltage. So this is about the effect of unbalanced stator voltage. Now we will discuss the second point, that is single phase operation of the induction motor with single phasing. Single phase. So here in the single phasing, again I will show some documents. So you can see here, this is what the single phasing operation with a single phasing. Now in order to have this particular single phasing directly, so for single phasing uh, operation, the equivalent circuit will be like this, will be like this. So you can draw this particular equivalent circuit. So for the single phasing, the equivalent circuit of the motor will be like this. So this is the equivalent circuit for the motor. So we can draw this particular. For single phasing operation, the equivalent circuit will be like this. So this is the stator resistance and stator leakage reactance. Now it is again the rotor reactance, again the rotor resistance, again rotor resistance divided by 2 minus S, again it is rotor reactance and stator reactance, then the stator resistance, it is voltage. So this is somewhat the equivalent circuit for a single phase. So now what is this single phase? So whenever the induction motor, three-phase induction motor, so it is uh, operated, and suppose the one phase is open circuited, then it is called as the single phase. So if there are three phases, so out of three phases, one phase is open circuited, then it is called as a single phase. So what happens here is that uh, whatever the three phase induction motor is there, so it is having A, B, and C phases, and the rotor is, it is cage rotor. Let us say it is cage rotor. So the three phase are connected to the power supply. The three phases of the induction motor are connected to the power supply. Stator, in the stator diagram, you can see if out of three phases, uh, one phase is open circuited, one phase is open circuited, then there will be single phasing. There will be single phasing. So at that time, whatever the VP is there, that is positive sequence voltage VP, that is equal to the negative sequence voltage. So under the single phasing, whatever the Vp is there, it is equal to V. P is equal to V. So uh, In is equal to minus Ip. In is equal to minus Ip. That is, whatever the negative sequence current is there, it is equal to the uh, minus of Ip. Minus of Ip. So when we uh, open circuit one phase, it is basically a single phase induction. It is basically a single phase induction motor. So we have forward feed as well as we have the backward feed. So it is no longer a three-phase induction motor. So when we are saying it is single phasing, then it is a single phase induction motor having two fields. One is forward feed and second is the backward feed or the reverse feed. So we have forward feed which rotates in the forward direction and reverse feed which rotates in the reverse direction. So this circuit mainly gives the equivalent circuit for the single phase induction motor. So in this case, the single phase, that is V voltage, is applied here, and this is split into two. So this is one, and this is another one. This is another one. So in this case, there is a single phasing. So there are two fields. One is forward feed, and another one is reverse feed. Reverse feed. So uh, here we have to calculate two slips, one for the positive field and other for the negative field or the reverse field. So again, as that in the unbalanced, so the positive slip, that is sp, positive slip, that is sp. See here you can say this particular, this is yes, this is yes, this is for the positive slip, SP, positive sequence will be S, and the whatever the 2 minus S is there, it is for the reverse field, that is for the uh, negative uh, sequence component. Negative sequence component. So there are two slips. One is SP, that is equal to S, and another one is the 2 minus S, that is the negative slip. This is the slip for the induction. Again, if I say torque slip characteristics here, so you can draw this torque slip characteristics of the induction motor, single phase induction motor. It is, so it is, this is positive sequence, this is curve is positive sequence, this curve is positive sequence, and this is for the negative sequence, this is for the negative sequence. So what will be the net torque here? So again, net torque is reducing, net torque is reducing, this is net torque, it is reducing. So there are two torque. One is the positive torque. One is the positive torque. You can see this is positive torque, and there are, again there is one more, that is a negative torque. So the resultant torque, again it is reducing. Again it is reducing. So this is about the single phase. This is about the single phase. So now we will discuss the third point, that is unbalanced rotor impedance operation. Unbalanced rotor impedance operation. So in this case, directly the speed torque curves with the unbalanced rotor resistance. This is again omega m. This is T. Again, unbalanced rotor resistance. Whatever the rotor resistance we are having, so it is unbalanced. So this is the positive sequence curve we are having. This is the negative sequence, and this is the net uh, curve we are having, net torque we are having. So now, what is that unbalanced rotor impedance operation? So earlier, unbalanced rotor impedance operation were employed for starting and speed control. They are not in use anymore. However, a loose contact in the rotor circuit can cause unbalance in the rotor resistance. So loose contact in the rotor circuit can causes the unbalance in the rotor resistance. So it is therefore useful to examine the effect of unbalanced on motor performance. So whenever there is a unbalanced in the particular rotor, then we need to examine the motor performance. So unbalanced rotor impedance operation causes unbalance in the rotor currents, whatever the IR we have discussed. The unbalanced rotor current can be resolved into positive and negative sequence components. It can be resolved into positive and negative sequence component in the again a single phase. Positive sequence rotor current produce driving torque in the same way as in a motor with a balanced rotor resistance. Balanced positive sequence will produce the driving torque. Again, the negative sequence component produces a rotating field which moves with the respect to rotor at a speed minus s omega ms and in space at speed of omega ms into 1 minus 2s 1 minus 2s. So this field induces current in the stator. Whatever the second component is there, it will induces current in the stator. So the interaction between these currents and the negative sequence rotor field produces a torque. So produces what? The torque. So for, let us say, S is let us say more than 0 or less than zero point 0.5, the speed of negative sequence rotor field is positive. The speed of negative sequence rotor field is positive. Therefore, interaction between this speed and stator current induced by it produces a positive torque on the stator, and consequently a negative torque on the motor. Thus, for again the slip greater than 0, less than zero point 0.5, the torque acting on road is difference between the positive and negative sequence torques. Similarly, it can be explained that for the S greater than zero point 0.5, less than 1, the two torques added. So whatever the figure is there, it mainly shows the nature of the motor speed characteristics. A large dip in the torque occurs. The large dip in the particular torque occurs at half of the synchronous speed. Half of the synchronous speed. So this is say the speed of the particular uh, motor. So whatever the large dip you are seeing, so it is occurring at half synchronous speed. So the extreme case of rotor unbalance arises when single phasing occurs in rotor. Single phasing occurs in rotor. So these are both whatever the uh, unbalanced rotor impedance operation and the particular single phasing, they are same. The extreme case of rotor unbalance arises when single phasing occurs in rotor. In this, torque developed by the machine at S is equal to 0.5 will be 0. S is equal to 0.5 will be 0. And motor may not accelerate beyond sorry this point in the starting. So this interaction between the positive and negative sequence component produces pulsating torque with the zero average values. So here, the presence of negative sequence component while reduces the motor torque, copper and core losses are substantially increased. So consequently, the efficiency and motor torque capability are substantially reduced. So due to this, the efficiency of the motor will decrease. So this is about the third point. What we have discussed is unbalanced rotor impedance operation. So here we have completed the 3 points. The first point is the operation of the three-phase induction motor when it is supplied with the unbalanced voltage. Second is the single phasing, and the third is unbalanced rotor impedance operation. So in the next session, so we will discuss about the operation of the motor when it is supplied with the non-sinusoidal voltages and some braking methods. Thank you.